Okay, in this video, I'd like to talk about receive filtering, and I know this is a revisited topic. All right, so if you remember, it seems like a long time ago, but before the break, we were talking about receive filtering, and then I said, okay, time out, let's put this on hold a little bit. Let's do exam 2, and then come back to receive filtering so that we can more thoroughly understand the significance of why this is an important topic. Okay, so right before exam 2, we talked about an optimal receiver filter, and I went through the math and showed you using dot products and a few other things, but we derived the fact that the matched filter is some gain constant k, and it turns out k doesn't matter. You can use any k that you want. We're going to use that fact when we scale filters so that we get the right maximum value for the symbols. All right, so you'll see that later in the Matlab code. But you can scale this to any k times the time reversed version of the pulse. Okay, so when I have n minus k, that means time reversed. Okay, so h of n is, that should be an n. Okay, so that should be, if h of n is the impulse response, then the impulse response is given by the time reversed pulse, where n is the length of the pulse. Okay? In MATLAB world, this would be a really simple command. H is just flip left right of the pulse shape, and times some scale factor that we might, not k, but I use k here, sorry. We'll just call this scale factor alpha. All right, so I told you this is optimal, and what we did in class is we proved that it's optimal in the sense that this will maximize the signal-to-noise ratio at the downsampling times. Okay, so you should know that. And then another thing you should know is that in general, filtering can create intersymbol interference. So in this Matlab demonstration, we're going to first concentrate on triangle pulses, and you'll see you start with a pulse shape that has no intersymbol interference because it doesn't extend over into adjacent symbol intervals, but the filtering actually creates some intersymbol interference. But if you're restricting it to triangles, you can still have a Nyquist pulse because at the downsampling times there won't be intersymbol interference. Okay, and later on, we're going to get to where we start using square root raised cosine pulses. Okay, so the square root raised cosine pulse, you should know, this takes this idea of filtering creating intersymbol interference, it takes it into account. Okay, so what's kind of ironic is you start with a pulse that's not Nyquist. All right, so we'll see examples of this when I do some Matlab examples. You start with a pulse that's not a Nyquist pulse, there is intersymbol interference, then the filtering actually generates a Nyquist pulse. Okay, so P starts out not being Nyquist, and then because we know what happens with the optimal filter, we can rig it to where after filtering you get a Nyquist pulse. So we'll see that with some examples. Okay, so now let's switch over. I want to do a Matlab demo where I'm looking at pulse receive filtering using triangle pulse shapes. Video. At this point, I'd like to walk you through Matlab code that looks at pulse receive filtering. Okay, so what we're going to do here is we're going to generate some symbols. We've done this many times before. And we'll have an upsample factor of 10. And we're just generating, in this next few lines of code, we're just generating a pulse shape. We're going to start with a triangle pulse shape, although we can change that. And notice it's self-contained within a symbol interval. The symbol interval is 10. The length of the pulse shape is 9. So there shouldn't be any intersymbol interference. This is definitely a Nyquist pulse because nothing extends out into the other symbol intervals. Okay, so we filter that, generate our shape, our pulse shape for our message, just like we've done many times before. Okay, so what I'm going to do is I'm going to compare this, where you don't do any receive filtering at the receiver end, and with the case where you do some filtering at the receiver end. So we just talked about that doing receive filtering improves the signal to noise ratio. We're going to walk through this example to explore this. All right, so the first thing I'm going to do is I'm going to put up a pulse shape into a subplot where you can see what the eye diagram looks with no filtering. Okay, and then the next thing I'm going to do is I'm going to do some receive filtering. Now, in general, receive filtering can generate intersymbol interference. But I've chosen this triangle shape. The original triangle shape is contained to one symbol interval. And so if I convolve a triangle with a triangle, that spreads that out to take up two symbol intervals. Follow my mouse here, it does that kind of shape. And because it only is self-contained to two symbol intervals, the pulse itself generates some intersymbol interference, but if I sample at the right time, I can do that without intersymbol interference. So you'll see that from the eye diagram. So we'll do a subplot with the filter turned on. Okay, and then for comparison, we're going to take a look at what happens when you have random noise. Okay, so this is a noise parameter for the homework on this, or the quiz on this video. I'm going to ask you to play around with this parameter so you'll be able to explore what happens as you add more noise. Okay, so we're going to generate a signal with some noise on, the filter is off, and then we'll do one with some receive filtering that's supposed to help with noise, and obviously we'll filter the noise in that case. All right, so what we're doing here is we're looking at an eye diagram when you have noise added, okay, and we'll do the subplot for that. And then what I want to do is I want to check the signal to noise ratio. But to check the signal to noise ratio, you have to downsample the signal to look at the power of the signal at the downsample times. Okay, so we'll see from the eye diagram when I get the figures up. I'll show you in a second. But we start sampling at 5 for the no filtering case. And when we turn on the filter, we're going to need to start sampling at 9. You'll see that at when we put up these figures. Okay, so from here, I use a receive filter, and remember the receive filter is the same shape. You just flip over the pulse, time reverse the pulse. But with a triangle waveform, and actually with all the waveforms we use, they're symmetric about the y-axis, and so flipping it generally produces the same shape. But that's just an aside. All right, so we generate the filter. One step that I need to do is I need to scale the filter so that I don't generate pulse shapes that are actually bigger than our symbols. All right, if I just didn't take care of the scale factor, I would get pulse shapes that are too large, right? We want symbol values to be 3, 1, -1, and -3. Okay, so I take care of that in this step right here. Okay, I convolve the filter with a time reversed version of itself. I'm sorry, I convolve the pulse shape with the time reversed version of itself because that is the optimal filter. And I look at the maximum of that and scale the impulse response of the receive filter by that value. That way, the pulse shapes have a maximum value of 1 after we do filtering. Okay, so at this point, I have a signal. All right, I've added
in the case where I've added noise to that signal. I can do the receive filtering, and I can look at the different cases. All right. One final thing before we start looking at plots. Once you downsample, you can do a decision diagram, a soft decision diagram. And since I know the symbol values in advance, I can color code those so that we can see when errors happen. All right, so you can go through line by line of the code, but some of this is just to get the plots to look right. All right. Okay, so when I run this, I get the symbol diagram. Let's pull up this result, and talk about this piece by piece. All right. So in this upper left corner, this is an eye diagram. Remember, I'm doing triangle pulse shapes. Okay, so you can see all the symbol values showing up, and it's clear that when I downsample, I should downsample starting at 5 in steps of 10. Okay, so we've done this many times. All right, once I do filtering, visualize this. You have a triangle, and you convolve that with a flipped version of itself. A flipped triangle is still a triangle. So when I convolve it with itself, you get this kind of parabola shape. All right, so you can see it has generated intersymbol interference because, over here, none of the pulse shapes change. It's triangles everywhere. Nothing, there, the pulse is contained to the symbol interval, so there's no intersymbol interference anywhere. Okay, but once I do the receive filtering, I generate a pulse shape that now bleeds over into 2 symbol intervals, which, at the non-optimal sampling times, that's creating intersymbol interference. But if I restrict my sampling to the optimal downsampling times, you see I get my pulse shapes showing up. My symbol showing up 3, 1, -1, and -3. Okay, so this is what it looks like without any noise. All right. So the next line here is, let's turn on some noise. All right, so now I have this noisy kind of eye diagram, and you can see the effect of noise. It kind of blurs the lines here. The eye is still open at 5 and 15, but if I keep adding noise, it's going to close the eye. All right, so what I'm wanting to do with receive filtering is to try to improve the signal-to-noise ratio. So if you go back to the Matlab code, I actually make an estimate of the signal-noise ratio where I look at the downsample values and I square them, and I divide that by the noise, the filtered noise. Okay, I have to square that too. So I look at that, convert that to dB, so that'd be 10 log 10 of the signal power is in the numerator, and the noise power estimate is in the denominator. Okay, so I get an estimate of what happens to the signal to noise ratio. Okay, up here, there was no filtering, so I just take the noise and square it. I didn't do anything to it, and so there's no filtering of the noise because there's no receive filtering, no filtering of the downsampled signals because I just downsample those and calculate the power. All right, so going back to the figures here, I can zoom in on this. It's kind of hard to see, but in the case where you have no receive filtering, the signal-to-noise ratio turns out to be 11.1 dB. After I filter, 16.6 dB. So you can see it did definitely improve the signal-to-noise ratio. Okay, you can also take a look at this and you say, wow, yeah, I can see that with no filtering, here is my soft decision diagram.
I didn't get that. Could you try again?
And I'm getting a little bit of spread, but the eye is still open, so there's still a gap between different symbol values. Okay, and so I put down here the probability of error for this particular noise situation. So even with no filtering, I'm not generating any errors with this level of noise. Okay, so this is a little bit tighter. The red doesn't have as much variance, the blue doesn't have as much variance, and so forth. This is better, but both cases are performing adequately well. Okay, so what I can do then is I can take a look at the noise parameter and start tweaking that and seeing what can happen. All right, so if I turn this up to say 0.6, all right, if I change this to 0.6, here is the soft decision diagram. Looking at the eye diagrams, I see in the case where I have, you can see a little bit of gap between here, but you're wondering, am I going to be able to communicate here? The signal to noise ratio is 1.19 over here with the filtering. If I add some filtering, I'm starting to see some space in between the waveforms in the eye diagram. Okay, so I've improved the signal to noise ratio. And I look over here, I see at the top, whenever I'm looking at the unfiltered case, some of the symbols are overlapping, right? And of course, that's generating errors in the communication system. So, the estimate coming out of the code here is this is 7% errors, which is terrible for a communication system. And in the case for receive filtering, we knock the errors way down. This is still probably unacceptably high for a communication system, but you get the idea. Lots of errors here, much fewer errors after we do this receive filtering. All right, so that's why that's an important step. Okay, so in the quiz, I'm going to ask you to tweak these values. When I run this, 0.5, I get 0 errors for the case where I use the match filter, and 3% errors in the case where I don't. Okay, so I'd like you to play around with the noise parameters and get a feel for how this happens with receive filtering.